So my name is Warren Togami, and I'll be talking about exchange security, not only protecting like the people, but also the business. This has been a topic of interest recently. So I have some credibility when it comes to security, largely from my previous career in open source software, where I've been working on the Linux operating system, first with Fedora and then Red Hat for many years. And kind of related to security is a problem of open source spam filtering. After that, I did an MBA and various of security consulting. I later became a Bitcoin developer. A few years ago, I was one of the 3 co-creators of the Scaling Bitcoin conference to bring this like academic rigor to the Bitcoin industry. I hope all of you are attending that conference from tomorrow. And in 2015, I joined Blockstream. I happen to work at that company. We do things relevant to the crypto exchange industry. But this talk has nothing to do with Blockstream. So a general problem, especially with the business type people, is that they see all of this marketing for security products and security brands, and they do not understand that security is a process, not a product. It's not something that you can buy. It is a philosophy or a culture practiced by the people. It's far more than only the technology within a company. And with ordinary business, like security is often not taken seriously because you can often recover from mistakes or errors. But when it comes to cryptocurrency, errors are not reversible, so the consequences are far more dire. Now, security can slow down feature development, but if you are lacking security, then your years of hard work can be instantly destroyed. So I'll talk about a few recent hacks from this industry. Like what happened in these incidents, and the later slides will be about mitigation measures that could guard against these sorts of attacks. So in 2012, this is very early in the Bitcoin industry, there was an exchange called Bitcoinica. I wasn't around in Bitcoin back then, so like this is only what I read from Google, but apparently what happened was a virtual machine provider called Linode, their customer service infrastructure was hacked, and the attacker searched for any reference to Bitcoin among their customers and targeted the virtual machines of 8 customers and stole all of the Bitcoin they could find in there. The largest of which was an exchange, and were robbed of 43,000 Bitcoin, which now is a lot of money. So I talk a lot more about cloud security a bit later. 2014 was a incident where spear phishing, or a targeted email attack, was used to compromise the email of the executive at BitPay, and then the attacker was able to see that the way Bitcoin transactions were manually authorized was with was with email. So using that, they sent fake email and tricked the executive into sending 5,000 Bitcoin to the attacker. And the details of this hack were later released due to a lawsuit between BitPay and their insurance company. So that is along the lines of a combination of social engineering, like fooling someone, and targeted attacks at like someone's browser or an email client to compromise their system or their email account. 2015, there used to be a prominent altcoin-only exchange called Cryptsy, and where exchanges like this would add every altcoin in existence with no quality standards. And unfortunately, one of these altcoins had a backdoor, and they had a lack of isolation within their server infrastructure, and this led to total compromise and theft of the other coins. Now, these examples were known in public. I happen to know other examples of hacks that were detected and thwarted before damage happened, where an entire data center was targeted to go after one customer. But luckily detected quickly and no losses happened. Or a very common attack in this industry is mobile number porting theft. In fact, I know several people in this room have been targeted by this attack. It's not only the people at an exchange or people who work on cryptocurrency software, but like even non-obvious targets like their spouses. Because like they're trying to get information in order to use in social engineering attacks against the people involved. Or I heard of an incident where email Trojan was sent to an engineer and managed to compromise their laptop, but luckily due to precautions inside their company, this was caught very quickly. So this is a survey of things that I'm aware of. There are many other examples, and I'll go over risk mitigation measures. Only some of the exchange hacks over the past few years. There are many other considerations when it comes to security, and I skip over some of the really obvious ones like physical security. So in those examples before, I talked about detection as one means, and like for those who do, who have done system administration, a thing that I often see is that they will only set up the server and the application such that it works, but then that's where they stop. Or maybe they'll lock things down to be a little bit more paranoid about what the application is allowed to do. One of the names of this is called the least privilege principle. The most common example of this is with firewalls, where you close everything, like all of the TCP and UDP ports, and then you open up only what you expect the application to do. So like a web servers and port 80 and port 443 only. Now, for incoming connections, that's where most sysadmins stop. But if you are really aiming to protect your infrastructure, then you want to go even further than that. And, for example, block all outgoing connections except for the specific resources that the application or operating system actually needs. And that requires a bit more research and testing. So similar to network level firewall lockdown with least privilege, there are even more fine-grained means of locking down resources with mandatory access controls. Like a very good mechanism in the Linux operating system is SE Linux or Security Enhanced Linux. It's also known as that thing where people will install Red Hat or Fedora and immediately turn it off because it's a pain. But it doesn't take that much to learn how to customize these roles. And in the documentation, it even shows how to set the SE Linux to permissive mode, where it'll only record what the system is actually doing, and then you can keep a log of all the resources that the application uses. And then you can run that log through a tool that will spit out rules for you. And then you can apply those rules and change it to enforcing mode. And that's not I would say that's like a 99% improvement, because if your production system is running in this way, where the application is locked down to only what it's supposed to be doing, then you could be monitoring the logs, and anything that deviates from that behavior will look suspicious. So another risk mitigation measure, okay, so like this is just like general security for any company. There are some things that are very specific to our industry because errors are not reversible. And there are some types of issues where exchanges can become insolvent even without a hack of the exchange. Because we are all so blindly reliant upon software made by other people. And the quality of that software differs substantially. So, so just one example out of many from last year, the Ethereum parity wallet, you know, multi-signatures is supposed to be more secure, but if you were using the parity multi-sig contract last year twice, all of your money was stolen or destroyed. And I haven't heard of exchanges losing money this way, but lots of ICOs lost a huge amount of money. And like this kind of thing can easily happen again due to errors. And the safety culture of how these systems are engineered. So in normal software, the default is to write the software quickly and patch it later. And for ordinary companies, maybe that's okay because you can recover from problems. But when it comes to cryptocurrency, I say this is an unacceptable attitude. And there are other types of engineering where this has been understood for a long time, like in aerospace. Like look at the history of rocket boosters and like how many of them explode at launch, or 1986 is the famous example of the Challenger space shuttle explosion that was later found to be, well, I like the way Nick Szabo put it in this tweet. What happens when managers and investors ignore the engineers and scientists? In this tweet from 2015, he's talking about Bitcoin, but using Challenger as a metaphor. So blockchain's transactions are not reversible. The purpose of business is supposed to be business. The payment tech must be boring, and a safety-critical engineering process will minimize that risk. And that's why I talk about the Bitcoin philosophy of don't trust, verify. A goal here is to minimize the need for trust. And for years, I've been visiting exchanges and talking to people that work at exchanges, and a very common problem that, like many of the way people have implemented exchanges, especially years ago, is to query their deposit addresses against third-party block explorers to look for deposits. Now, there's problems with this, largely of the type of you are trusting someone else's system, and while only you are responsible for losses. And if you run your own full node, then the cost of automated verification is super low. So why trust a third party? There are other elements to what I believe is the true meaning of don't trust, verify. And I think that like this, as a philosophy, it underlines the Bitcoin engineering approach, and like it's not well understood outside, where like Bitcoin is criticized for moving slowly. Well, there are reasons for this that have to do with the peer review process. So if you look at the pull requests in GitHub, which is how code changes happen in Bitcoin, you'll find examples. I think like people in this room have a pull request 9622 that took 7 months and 120 comments. So this pull request chain state DB, which turned out to be very important for security reasons later. 245 comments. Like this is like only just examples of the extreme level of care used in Bitcoin engineering. Or SegWit, 14 months between design, implementation, review, and deployment in a version of Bitcoin Core. Or even outside of the Bitcoin industry, people are aware of the security disaster that OpenSSL has had, where I think OpenSSL was the beginning of brand names for security vulnerabilities, Heartbleed. And this revealed that OpenSSL actually had many other security issues that needed a lot more attention. And the thing is, the Bitcoin devs knew this years before and had begun on a very narrow replacement for OpenSSL inside of Bitcoin Core. And it took years of review and even some formal verification for them to be confident that they have a high level assurance, because like the usual rule in software engineering is you do not roll your own crypto. It's very dangerous. Well, sure, but you can do it very carefully and narrowly. And by eliminating OpenSSL, they reduce the attack surface. So the first step of defending a company is to defend the people. And I gave like examples of those exchanges hacked by tricking people into opening emails that they shouldn't, or like social engineering attacks like are typically used against like a phone company in the US to steal someone's phone number. It's very hard to defend against that. So for example, if you're using a mobile number as a second factor authentication to log into services, I know people that have like a second unlisted phone number under someone else's name that they use for that. Because you can't be too careful, especially when you're in this kind of industry. Or computers, Windows, Mac, Linux. The attack surface is very large, and like copy and paste, especially for cryptocurrency addresses, can be very dangerous. So the defense for end users, not only for wallets, you know, like the Ledger or Trezor, but also for two-factor authentication logins used by wallets like Green Address, Greenbits, or like there were hardware two-factor solutions. There's a standard called FIDO that's implemented by, like this is Google's Titan key, and another popular brand is YubiKey. You probably want to lock down your Gmail account with this type of second factor security if you are in this industry. And I don't have a good picture for server-side hardware security, but I show a little more fun example. I think earlier today Taj was talking about Lightning, but then like a drawback of Lightning is that the receiver needs to be always online with the private keys. And that can be bad because computers can be hacked. So that's a picture of the Lightning Network from like the middle of this year. It's probably much bigger than that right now. Like the website where I got this is gone now. If someone has a better website, I'm interested. So earlier, okay, March of this year, like someone took a little system on chip and made this into a like hobbyist Lightning node that isolates from the main system that's on the network, the private keys. And you could program a thing like this. Like I personally worked on hardware like this in order to separate like a private key signing from a server for different use cases. And you can program rules into this. For example, only sign if the Lightning balance would go up. There's some exceptions to that when it comes to balancing, which makes it more complicated. But so in general, when I mentioned the isolation of different software or hardware is very important. And like the biggest example or the easiest example to use is the Cripsy hack from a few years ago, where you really have to be careful about the software you download from other people. And I think in the case of this altcoin, even the backdoor was visible in the source code on GitHub. I'm not sure about this. But it's easy enough to hide backdoors and only the binary, and it's not visible in the source. But the information that the experts at the time heard is that the security practices inside of Cripsy were very bad, where they were running all of these altcoin daemons on the same machine, maybe even the same non-root account. I'm not sure about that one. So like this is like very basic and obvious like security isolation measures that you should use, and like I would design things such that you not only trust not only do not trust third-party software, do not even trust your own software. And that's where I recommend the least privilege. And like there are all sorts of examples online better than this, but like to create security zones in your systems and one-way logging where you have a notification system. So the examples earlier of hacks that were detected were because of like audit logs and notifications to detect unusual behavior. And you want these to be as separate as possible. Okay, I'm astounded how people do not talk about the extreme risk that the cloud has. I've been working on operating systems for now 2 decades, and while working at that company, I witnessed over and over again exploits, like local exploits of the hypervisor, container breaks, and like this happens over and over again. And recently there's Meltdown Inspector, which also were complete breaks for a virtualization. Like the idea of the cloud is you are sharing like virtual machines, like resources on physical servers, possibly with other customers. And any of those other customers of your hosting provider could break the physical security and get into the other customer's data. And this is like even worse for containers. Virtual machines have never been secure all these years either. But the reason that companies use the cloud is because actually it's very convenient and it's great for rapid development. I entirely encourage, like the current practice of developers using the cloud for prototyping and testing in non-production instances of their system. It's okay. It's great for on-demand capacity. Great for cost control, but keep in mind how this industry differs from most normal software. We cannot recover from errors. So in general, you need to be aware and to appropriately design isolation between systems, keeping in mind that that virtualization simply is never secure. And the cloud industry is sort of aware of this. Like, I would stay away from the public clouds, like ordinary AWS, or like in the case of the 2012 Bitcoinica hack, that was a hack of the Linode service provider, one of the earlier, like very convenient virtual machine providers. Like knowing full well how dangerous these things are, some countries demand that the cloud infrastructure be hosted in their country, and like the people in the company who manage those resources that they sell to governments like have security clearance for that country, and like you have to trust that the provider doesn't mess up. It creates a larger attack surface for an insider attack. With a bunch of people you don't know, by trusting these so-called secure clouds. Maybe it's good enough, I don't know. Well, like these things are secure until they're not. So I have friends that work at, you could call them traditional payment companies in the United States. And like the consequence of a hack there is significantly smaller and recoverable in many cases, but they do not host their infrastructure in public clouds at all. It's only in-house servers. And there are platforms that give you all of the convenience of cloud for your developers, for internal use, but on your own hardware inside of your own company. So then you need to trust only insiders of your company, and hopefully that's safe. Now keep in mind, it's secure until it's not. And other popular things for developers are like Node.js, NPM, Golang, GoGet, is it? Rust is, I can't remember now. So these are very convenient libraries to, you just add them as dependencies to your project, and then it'll automatically download usually the latest version of that dependency. And the problem is you have no idea what you're downloading. And you did not audit this code in control of other people. The download infrastructure may not be safe. There are very paranoid ways of using this, like, for example, in Node.js, you can have in your packages.json, you can lock it down to specific hashes of particular versions. But nobody does that. And like a related issue, this was last year for a while, like there were Trojan things in the NPM library. I don't know, like I think there was even one case of like not of mainstream modules being compromised, but I'm not sure about that. Okay, so I talked about danger of third-party, okay. So another attack that always has been an issue is being able to hide backdoors in binaries. Now, the first step is like verifying if the source code is compromised. Now, no one checks the source code that they use, but maybe with careful peer review of the software that you use and the signed commits and like knowing the people involved, it's kind of like social proof that the source code is maybe safe. But identified quite a while ago was that it's possible for entire operating systems and compilers to be compromised in a way that's not visible in the source code. One of the famous papers on this is by Wheeler in his 2009 dissertation. And there are different ways to guard against this. They're not easy, but the Bitcoin developers were among the first to take this as a serious problem, or to treat it as a serious problem, and pioneered a tool called Gideon, which the goal is to make binaries bit for bit reproducible, no matter who builds it. And Gideon is pretty good, but still not safe, because it blindly downloads the latest version of Ubuntu and uses that to build, and you have no idea what's in there. So due to this, the Bitcoin developers have been aware of that risk for years and have been working on a next generation deterministic build tool chain. There are people in this room working on this, and other people attending Scaling Bitcoin in the next 2 days. They're not ready to announce yet, but like this is, as our industry deals with larger and larger amounts of money where things are secure until they're not, we need to be especially careful about like the chance of this kind of compromise happening is very low, but it only has to happen once. Oh, and not in my presentation is the is the risk of hardware attacks. In the news yesterday, there was a Bloomberg article about state-level attacks where a chip was inserted, not part of a design, into motherboards. You know, like it takes a lot of time, effort, and money to do that, but to be able to trust the supply chain of hardware, that's the problem described in that article. I'm talking about the supply chain of software here. And we need to be able to fix all of these problems as we deal with larger and larger amounts of value where mistakes are not recoverable. So you also heard earlier today about atomic swaps and trustless exchange of different types. So I don't have to talk too much about this. This is the future. Especially when you see like time and again exchanges in the past custodial model who are responsible for customer funds getting hacked and losing it over and over again. This runs the risk of regulators panicking and creating rules that are more and more draconian. And that makes me wonder if the industry will be able to move more towards a trustless model that shifts the liability to personal responsibility of the owners of the token. Okay, so here's another say crypto industry specific problem. So when we talk about full nodes and don't trust verify, we want everyone to verify for themselves. And that's great if it works. The risk of consensus is if your view of the truth differs from other nodes. And this can happen, for example, with a Sybil attack. No time to explain it right now, just look it up. Or alternative implementations have, there's a debate for years about the wisdom of this. Now, the problem with alternative implementations is that they must be bug for bug compatible. And it's really hard to be bug for bug compatible when bugs are not yet discovered and over the past few years, we keep finding more and more of these behaviors, like the BIP66 strict DER encoding bug due to unexpected behavior in OpenSSL is one example from Bitcoin history. Where even two versions or two Bitcoin core nodes can disagree with each other. So like probably the best we can do to guard like your company against this kind of problem is just to have paranoid diversity of verification. It's like you can use any of the full nodes that you are most comfortable with for your company, but you also want to check with a whole bunch of different full nodes out there, like in your network, outside of your network, different implementations, older versions of Bitcoin D, your friend's node that is not managed by you at all. And if they disagree, then you may want to put a stop to certain parts of the business automatically until humans can investigate. Like, it's a disaster if you accept a deposit and through a flaw or attack, your view of the truth differs from others, and a trade happens and they withdraw in some other currency, and then your exchange is left insolvent. Okay, so what I've done in my career for like 20 years in open source is not only the development of the software, but also like organizations and projects to help the industry and the community to do a better job at this. So a few years ago, I was a co-creator of the Scaling Bitcoin conference series. And a more recent project with a few people in this room and other people in the community and industry is we're launching a education project. It's very simple. The Bitcoin developers choose or write articles that explain something that's misunderstood, and then it's translated very carefully into the major languages of the world, especially languages where English is not very strong, and in some of these countries there are not a lot of experts, or there may be experts but they don't have time to explain things. So if you are translating source material of facts from the experts very carefully, this sort of material would be quoted and used as source material in the media and all sorts of things in this country. And that's how, like, this is very useful for developers in these countries to better understand and learn and to get more involved. It's an opportunity for non-developers as well to learn more and to be able to help in the industry. So in this room, I would like to introduce Ruben Samson, who's the education director of Reading Bitcoin. We are creating a nonprofit organization for this. We intend to be working with the Linux Foundation. The Linux Foundation has 160 other sub-foundations for various open source projects. This is not a software development nonprofit. This is only education. So there's a prototype website at readingbitcoin.org, and then you can click on the language selector and it shows what this site can be for Chinese, Japanese, Korean right now. We need both individual volunteers, corporate sponsors, and individual sponsors in order to do to do a good job of this. We tried to do this with only volunteers this past year, and to maintain quality of translations with volunteers is too difficult. So I would encourage you like to follow these accounts on Twitter, and then you'll see more news when, as we are bringing these online, and we need your help. Okay. So any questions?
As for using third-party libraries, is there any reasonable policy that you would recommend? Because not using any, that's going to be hard to sell. So where do you draw the line?
Of course, this is not a simple problem. Like, develop your application using dependencies, and then like, once it's ready for production, lock down to the specific versions of those dependencies and sub-dependencies of that, and then like skim through the code, look at the diffs of those individual projects over time. This is the sort of things that I've done at Red Hat, because, you know, like millions and millions of people are dependent on this software that we shipped in this open source operating system. And we don't, like, we also took tens of thousands of dependencies made by other open source projects on the, like, out there on the internet for the last 20 plus years. So, like, there's no substitute for doing as much careful checking as possible, but like really lock down to specific version numbers and even hashes of the dependencies, and it's really not easy. Yeah.
Okay, thank you.
Thank you very much for your talk. One of the big things that I've run into a lot with a lot of the projects that I've been working on is that if you offer a method for people to verify something, like for instance, GPG sign something, or so it's like if you want to trust us, then you can verify the signature, and then you'll know that at least it's what we say it is. And then the trust only relies on us. But if you're not verifying anything, then you need to trust to make sure that nothing happened between when it came to your computer, no one was injecting something, and all of these other things. But I do find that if you do something like GPG signatures, and then the users, 99% of them don't check the signatures because it's too hard, or blah, 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 or some reason, then their effective security gained by GPG signing is 0. So what are your thoughts on middle grounds for everyday users in the context of all these security methodologies that you've been talking about?
So the first answer is personal responsibility. Like, especially if you are an exchange, you are a service provider, or other people are relying on you. There is no excuse but to check. Now, for ordinary end users at home, normal personal computers and phones are not securable. You need hardware security to augment that. And the hardware wallets these days are pretty easy to use, and there's no reason not to use them. They do have a cost, but what's the cost of losing everything? Now, middle grounds in terms of like software you download, sure, ordinary humans do not verify GPG things. And ordinary humans do not use deterministic tool chains to verify that things are what they are supposed to be. But like Windows and Mac does, and like the way Bitcoin software is distributed in Windows and Mac are signed by keys that are registered with Microsoft and Apple. So that's a middle ground that actually works until it doesn't. Well. Microphone.
So let's assume it's 2020 and I'm running a Lightning node or a Lightning hub that has like millions of dollars in locked payment channels. What would you recommend for me to sleep well at night? I mean, what are specific measures would you employ when you have basically like millions of dollars in what's a hot wallet?
Physical security, very carefully maintained software operating system stack, checking for, like there's now open hardware that is not quite good yet, but there's like IBM released to Open Power that is pretty good, and it's a little expensive. Competing with that is RISC-V by a consortium with like Google and a bunch of companies that want there to be a royalty-free platform in the future that like that'll eventually be fast enough, but then like supply chain of manufacturing, I don't know if we'll ever be able to fix that with reasonable cost. But like things like this, it's like more than one computer and a very constrained communication between them that is very narrow can go a long way as long as you have physical security. Like it could just be two PCs with a serial cable between them.
And would you recommend that over a hardware security module with a custom firmware?
Well, if someone knows what they're doing, there's no easy answer for this, but like this example at least has the benefit of being something that is very cheap, that someone could publish all of the source code and the firmware for something like this, and the firmware can be peer reviewed. But for now, this is only at the hobbyist level. Any more? Okay. Yeah. So again, we need your help, the help of your companies, for the entire industry to do readingbitcoin.org together. Please approach myself or Ruben if you're interested in helping. Okay. Thank you.
All right, thank you very much. We'll take a quick 10-minute break before the next session. So we'll resume at 2:10. また10分の休憩を取りします。
Hello? Okay, guys, I think we're getting started. How you doing? You guys look kind of tired. Well, given your brains are probably fried, I'm delighted to tell you that this will be a pretty high-level talk. We're just going to try and get a general flavor for the way that Bitcoin Core is structured. I'm James O'Byrne. I work at Chain Code Labs with a few of the other guys here. I've been working on Bitcoin Core since 2015, and I'm in New York most of the time. What's going on? One sec here. There we go. Cool. So today we're going to talk about Bitcoin Core. It's going to be a pretty high-level conversation. So we're going to talk about what Bitcoin Core does in a general sense, what its particular user interfaces are, the concurrency model that Bitcoin Core uses. It obviously does a number of things seemingly at the same time. We're going to talk about regions of code in Bitcoin Core, how storage works, what the various data structures are that are involved, and some future work that you can keep an eye on. So Bitcoin Core does a number of things. Obviously, I think the most essential role it serves is to be a validating relay node in the peer-to-peer network. That is to say that it passes around blocks and transactions and maintains some notion of validity. It's also a wallet implementation, so it's a GUI and an RPC tool for end users who actually want to manipulate coins. But it's also a working example for people doing wallet implementation. So for example, Bitcoin Core right now has one of the most sophisticated coin selection algorithms, and that's kind of a reference implementation for other wallets that may want to follow suit. It handles block assembly and submission for miners, which is obviously important. Provides a programmatic interface for general Bitcoin applications, so block explorers, wallets, things like that. And it's sort of a reusable library for validation and serialization, but I mean, let's be honest here, not really. So in this talk, we're going to talk about the concurrency model. How do we do things simultaneously? What are the major subsystems in Bitcoin Core? How do we store and access data on disk? What are the major data structures or some of the major data structures? I'm going to gloss over a lot of stuff, obviously, because this talk is supposed to be 30 minutes, and I'm pretty tired, so I'm not going to go into a lot of detail on cryptographic implementations, peer-to-peer message protocol, the graphical code. Marco is going to get into the test framework and deterministic builds after I do. And I'm not going to talk about like exactly what defines validity in Bitcoin, or really anything detailed. So this is just about some of the concepts in the code. Hopefully you'll take the contents of this talk and go do some exploration for yourselves. So I'm hoping that this is just kind of a blueprint for you to go out there and poke around. So let's talk about the user interfaces. Bitcoin forms a TCP overlay network of nodes passing network messages to one another. Those messages, in case you're curious, are defined in a file called protocol.h. There's I think a struct named net message types that you can look at, and that's kind of a succinct summary of all the different message types that nodes can communicate to one another. Each node has a set of outbound and inbound peers that they exchange data with. You can manually add nodes with the add node flag. You can set the number of max connections that your node makes. Peers can be manually added, or they're discovered from DNS seeds. DOS protection is obviously a big part of the peer-to-peer protocol because if someone connects to you and starts flooding you with messages, you don't want them to be able to overwhelm your resources and take down your node. And simple payment verification nodes commonly things people use on their cell phones, query full nodes for Merkle proofs. So Bitcoin provides that. Another interface is the RPC HTTP interface. So this is just a general way for users to interact programmatically with Bitcoin block explorers use it, wallets, miners, and Bitcoin CLI is actually powered by the RPC interface. So the Qt interface is the graphical interface for Bitcoin. Who here has used Qt? Cool. Okay, who here has cloned a Bitcoin Core and just looked around at the code? Cool, okay. Who here has cloned the code and looked around but not actually used Bitcoin Core? Nobody, okay. Quick digression there. Another interface that's lesser known, I think, is the 0MQ interface. And this is kind of neat because basically we can get notified on a socket when various interesting things happen. So namely when we receive blocks or transactions. And that's just a little Python snippet kind of demonstrating a use of that. People build all kinds of stuff with this. I think like the Bitcoin fee bot and Bitcoin confirms. Twitter bots are built with this. So let's get into the concurrency model and start talking about the code a little bit. So needless to say, Bitcoin Core performs a lot of tasks simultaneously, and it needs some way of doing that. Basically, the way that it does that is it uses threads and some shared data structures. The data structures are guarded by locks. And it's a little deceptive because Bitcoin Core is like, in some ways is literally multi-threaded, but for many of the important operations it's not, because you're sort of contending for these locks. I'll talk a little bit about that later. A lot of the initialization stuff happens in a file called init.cpp, so if you want to look at that, you can see where all the threads are started, a lot of them. Peer-to-peer networking, in particular, is enabled by a select loop. So basically, we open a file descriptor for each peer that we're talking to, and we run the select loop over that to listen for read and write queues. Select may be replaced with poll someday, which is a little bit more of a verbose way of dealing with that. So like I was saying, basically all the changes to chain state or the active chain or the UTXO set are basically single-threaded because they're all guarded by this warm lock named CS main. So if you ever have three hours to kill, you can grep for CS main and check out all the places it's used. So next, let's talk about the particular threads that are involved here. So for the threads that we do run, there are a few like peripheral tasks that are taken care of asynchronously. So we do script verification using multiple threads. Basically, it's the minimum of either nproc or 16. We load blocks in a specific thread on startup. We service our PC calls, so we run a little HTTP server with 4 threads. We load peer addresses from DNS seeds on startup. We send and receive message to and from peers. We initialize network connections. We open added network connections after we start up. And we process messages that we receive from the network into kind of local state changes on our node. So we also run some threads for Tor control, for wallet notification. Does anybody not know what wallet notify and block notify do here? Oh, everybody knows. All right, cool. Well, they run commands based on certain events that happen, so that's cool. And we run this thing called the C-scheduler service queue, and it turns out that this sits behind something called the validation interface, which I'm going to talk about a bit later. And that's where we get most of the powerful asynchronicity in Bitcoin. So validation interface allows the asynchronous decoupling of chain state events from various responses. So basically, what I mean here is that anytime anything interesting happens, we connect a new block, or we disconnect a block, or we establish a new valid tip. You can register these callbacks that respond to those events. We actually use something called the single-threaded scheduler client to queue responses and execute them out of band with respect to things like network communications. Though again, we're still blocked on lock acquisition, so CS main comes up a lot here. It's used for a lot of things. It's used to build indexes, to trigger announcements to peers, trigger wallet updates, sending 0MQ publications. This is just a list of the various events you can make use of. So if you want to play along at home and do some stuff to find more out about the concurrency model, you can grep for C critical section, which is basically all the lock definitions, and trace thread, which is used whenever threads are spawned. So let's talk about something I call regions. Regions of code are basically little modules of state and procedures that each do a various thing for Bitcoin. It's not like an official term, it's just kind of what I thought to call it. Each region is basically a subsystem and it handles a certain domain of tasks. So looking at these things should hopefully give us an idea of the different granular things that Bitcoin does and where it does them. So in summary, basically the net region handles socket networking, tracking of peers. Net processing routes the peer-to-peer message that it receives from net into validation calls and other response peer-to-peer messages. Validation is probably the single most characteristic file in Bitcoin. Yep. Sure.
You commented that a large portion of the validation or the chain state code is under the one mutex.
Yep.
I'm just curious about your thoughts as to whether that is a major bottleneck and whether there's work to sort of alleviate that with sort of more fine-grained threading.
Yeah, there are a lot of discussions about how to potentially alleviate that. I think one proposal was to split CS main up into read and write locks, and so that's one avenue. But I think a lot of people think that's a bit more work than other avenues we could take. For example, like splitting CS main usage into more granular locks to kind of free up certain regions of code. In the future work section, I'm going to talk a little bit about the proposals people have for dealing with some of that and making different parts of the system asynchronous. I think it's important. It's not critical. I mean, your nodes are still running, right? So I think it's okay, but it's something that we'd like to improve. I think if there's something in particular that's motivated by, say, a particular approach to do initial block download more quickly, and it turns out we need to restructure CS main somehow, then, I think if there's a motivating reason to really rejigger it, then we can kind of get there. Cool. Any other questions while I'm before I jump into the region stuff? Okay. So, yeah, validation is really important. We're going to talk all about that. TX mempool defines the mempool data structure, which is basically where transactions that are unconfirmed hang out. Coins in TXDB define a view on the UTXO set, the unspent transaction output set. That's really important, and that ends up being where a lot of the performance bottlenecks of Bitcoin come in. Script defines script execution and caching. Consensus is kind of weirdly named and doesn't make a whole lot of sense. It contains a few consensus params and various things like how to calculate Merkle roots and some transaction validation. Policy is for fee estimation replaced by fee. Index is for peripheral index building, like TX index, if anyone's familiar. And wallets for wallet DB and coin selection, as well as fee bumping. So let's talk about net. Net's basically the bottom of the Bitcoin core stack. It's where all the socket-based network communication happens. It contains addresses and statistics on our peers. So that's C node stats and C nodes. And we keep various information on those for the purposes of figuring out who good peers are and who bad peers are, who is synced to what tip, things like that. CConman, which stands for Connection Manager, is the main class in this region. And that manages all the socket connections and network interactions for each peer. And it forwards messages to the net processing region via this thread message handler. So that's where a lot of the guts for the networking live. GConman is the global instantiation of the CConman interface. So in net processing, that's kind of like one layer up on the stack from net. Basically, net pulls on sockets and then reads information off of sockets, throws it into various attributes of the C node instances that we keep track of, and net processing then picks these up in another thread and kind of renders those messages into actions, whether that's calling into various functions or sending various P2P messages. So yeah, like I said, validation-specific data is maintained per node using C node state. And basically, if you open netprocessing.cpp, you're going to find one giant function called process message, which is basically a case statemented way of handling every single P2P message. So when we receive, for example, a block message, that basically translates into a call on process new block in the validation module, and so on and so forth. So peers are also penalized here based on bad behavior. So you can grep for misbehaving to see all the various cases where we're keeping track of bad behavior. So if someone keeps spamming us invalid blocks, obviously we want to disconnect them at some point. Validation handles modifying in-memory data structures for chain state and transactions on the basis of certain acceptance rules. So if you really want to get to the spirit of what Bitcoin considers valid, validation maybe obviously kind of contains that information. It defines some of the data structures that track this information, C chain state and map block index, and it contains procedures for validating them, like check block. Oddly enough, it also contains some utility functions that do things like marshal data to and from disk and populate the mempool based on some safe state. It turns out that validation is actually the vestige of a giant file called main.cpp that got split into net processing and validation maybe 2 years ago. And of course, it has the instantiation of CS main. So this is a little diagram just kind of showing how validation relates to the other regions here. So it has this chain state object that basically holds both the map block index, which is kind of like a map of the blocks that we've seen, as well as chain active, which is the the most work valid chain. And net processing calls into it in various ways, but this is kind of like from the perspective of when you receive a block, you're going to call a new process block at or process new block at some point. It interacts with these classes that are defined in TXDB. So C block tree DB kind of handles map block index, which again is like the tree of all chains and blocks that we've seen. And Ccoins view via Ccoins view cache handles what's called the chain state, which is the UTXO set. So I'll talk all about that a bit later. So in TX mempool, this basically just provides the definition for the in-memory data structure that manages the set of transactions that the node has seen. And it provides a helpful view of transactions sorted in various ways. For example, like by fee rate, by transaction ID, entry time, fee rate with ancestors. And that's basically so that we can do a bunch of things like fee estimation, like efficient block assembly. So keeping an index set allows us to pull in the highest fee package of transactions that we have. The mempool is a fixed size, so there's some eviction logic in there for booting transactions out if we need to. And an index of the UTXO set, which contains mempool transactions, is provided by a class called Ccoins view mempool. So these two files, Ccoins and TXDB, basically define the interface that we have for working with the UTXO set. Does anybody not know what the UTXO set is? Okay, that was a pulse check. God, you guys look so miserable. I'm sorry. So this is just a class hierarchy that defines the various ways that we can see the UTXO set. This is really important because, yep.
Sorry, I meant to ask a question 2 slides ago, but so this, with the blocks, DAT files, I remember a really long time ago, someone said on Stack Exchange or something like that, that blocks are not necessarily in order in the DAT files. And I was wondering, since then, headers first sync has kind of gotten into Bitcoin. But since headers first sync, would a newly synced blockchain be in the order of the blockchain as it is currently in the DAT files, or how does it write to the DAT files just as first come first written basis?
I think the DAT files only contain, let me think. So there's map block index. Oh wait, is somebody.
Okay. Okay. All right. There you go. Thank you.
Cool. So yeah, there are various ways we can access the UTXO set. Some of these are performance dependent and others aren't. So Ccoins view cache basically allows us to keep an in-memory cache that's as big as DB cache dictates it is, which is a setting you can pass to Bitcoin D. And that will cache some of the coins in memory, but if not, it'll fall back to the database. And then as I was saying earlier, Ccoins view mempool incorporates the existing UTXO set with the contents of the mempool. So basically, Ccoins view just boils down to this really simple interface for getting an unspent coin and asking whether we have an unspent coin. There's a lot of other stuff in there that's just effectively implementation detail. There's something called DB wrapper, which is an abstraction around how we deal with level DB databases. So I'll be talking about the different kind of storage mechanisms that we have later on in the deck, but yeah, basically the only interesting thing here beyond level DB access is that it allows us to obfuscate data, which we do to avoid spurious antivirus detection and various unsavory data from getting people in trouble who run full nodes. The script subtree contains procedures for defining and executing Bitcoin scripts. It maintains structures which cache script execution and signature validation. I think one of the most interesting parts of this region is a function called eval script, which is basically the script interpreter. So you can check that out if you want. Consensus is the aforementioned weirdly named region containing various things. I think it was like an attempt to consolidate a lot of what dictates consensus, but obviously almost everything in Bitcoin D dictates consensus, so it's kind of a weird name. But yeah, it contains various parameters. It defines the BIP9 deployment struct, which is kind of interesting. If anybody remembers from 2017. C validation state is in there, which is basically a little piece of state that gets passed around various places to accumulate DOS scores. Policy is another strange name for what this region does, but basically it just contains various utilities for making assessments about transactions. So it'll tell you if a transaction is signaling for replace by fee, and it also contains a big chunk of code for doing fee estimation. Interfaces is a kind of interesting one. This is a newer addition, but basically interfaces is the start of an enumeration of the various interfaces in Bitcoin. This is part of an ongoing effort by Russ Yanofsky to decompose different parts of Bitcoin into separate subsystems that communicate using more formalized messages. So initially, everything's still running in one process, but maybe one day the wallet and the GUI and the Bitcoin node itself will be running on different processes. Maybe they'll live in different repositories. So the first step in that is to enumerate out the interfaces that different parts of the systems use. So that's what's in there. Indexes is pretty cool. There's been a lot of work done on this lately by Jim Posen. Basically, right now, the only thing it has is the TX index. Does anyone not know what the TX index does? Right on. So the TX index basically provides a quick way to look up from the hash of a transaction into the raw data for the transaction. So it's a useful thing to have if you're a block explorer or if you're doing anything where you're doing a lot of looking around at transactions. There are some additional indexes proposed. So Marcin Jakimic did some work over the summer to implement an address to transactions index. And this thing actually makes use of that validation interface construct to perform index maintenance. The wallet kind of does what it says. It's logic for marshalling wallet data to and from disk via Berkeley DB, so I'm going to talk about Berkeley DB in a second. Contains various utilities around fee bumping, doing coin selection. It's the RPC interface is in there, and it's some bookkeeping stuff for wallet owners. Qt defines the graphical interface, and I'll shirk that completely. RPC is where all the definitions for RPC functions live, and this is I just kind of included a small example here, but you can see it's fairly easy to add an RPC command, so you can check that out if you want. Miner contains various utilities for generating blocks to be mined. The block assembler class is kind of interesting. Just pieces together a valid block given some parameters. And it's used in conjunction with various RPC calls by miners. So get block template is how you basically distribute a block template to a mining pool to get everybody coordinated on the same block. And submit block does what it says. So ZMQ contains that ZMQ interface code that I was talking about earlier. So let's get to the interesting stuff. Let's talk about data. How do we store stuff in Bitcoin Core? Here's a tree of the file structure. If you go into your data dir, this is what it looks like. So I'll pull out specific parts of this here. So the .dat files that were mentioned earlier in a question are basically just raw bytes of some serialized data structure. And you can check out how that serialization happens in a file called serialize. Basically, there's like a macro that's defined that you can use called add serialized methods, and then you can define a few methods that handle how data structures are packed and unpacked into raw bytes. So what are the various .dat files that we deal with? Well, obviously there are block files. Some relevant functions there, write block to disk and validation, and you can see how blocks are actually serialized in that method there. We have these pieces of undo data, and undo data is basically an optimization that makes doing disconnections and reorgs a bit easier. The idea being that we track the coins that are consumed by a given block, so that if we need to replay the chain or unwind part of the chain, we basically have a quick collection of the changes that we need to make to the UTXO set for that to happen. Mempool.dat serializes out the contents of the mempool so that we can shut down and then start back up and keep some notion of the mempool going. Peers.dat are serialized peers, so again, same idea as the mempool. And banlist.dat has the peers that we've previously banned. Let's see. So that's just highlighting all the .dat files there are in the directory. You can kind of see there's the ban list. There's some blocks. I generated this using regtest and fee estimates, mempool, peers, wallet. So LevelDB is another mechanism that we use for storage. It's a fast sorted key value store living on disk. It does some nice things like allow us to write in bulk, and it actually provides snapshots. So in theory, we could use this later to get like a snapshotted view of the UTXO set and pass that off to some peripheral process instead of having to lock CS main and access into the active UTXO set. It's actually bundled with the source tree in Bitcoin, so you can go and take a look at in the Bitcoin Core GitHub organization. There's a repo called LevelDB, and that's where we actually maintain an instance of LevelDB, and we will periodically merge from upstream. LevelDB has the block index, which again is the tree of all the valid blocks that we've seen, and it holds something called chain state, which is, in my opinion, a really confusing name. That's basically just the UTXO set. So those are all the LevelDB contents. I'm kind of whipping through here because I think I have 2 minutes. Berkeley DB is, in coarse terms, like LevelDB but worse. We still use it for the wallet, mostly because it's kind of we're trying to figure out a migration path, but basically we'd like to move the wallet data file to something else. The only thing that we use it for right now is the wallet. So what are some data structures? I don't know if I'm going to have time for this. What are some interesting data structures? You guys can go check this out if you want to later. Some advice for exploring the code base, which I hope you go home and do. I think it's really helpful to have some way in your editor to do go-to definition and a find all usages type thing. So there's a package called rtags that has rtags itself as a program, and then there are various bindings for Vim and Emacs and stuff like that. I find that really helpful. And then Bitcoin has this nice doxygen output, which I think is, that picture isn't displaying. But anyway, that's cool. Also, there's a document called the developer notes, which you should definitely read. So in terms of future work, there's an initiative by this guy, Jesse Cohen, to split out process new block from net processing and basically have net processing and validation communicate over this kind of in-memory message queue, which is kind of interesting. Like I said, Russ Yanofsky is working on separating out Bitcoin D into separate parts, and Corey Fields is working on some various refactoring stuff in net. So yeah, thanks. Yo.
So just to make sure that I understood, LevelDB is used to store the index of the blocks, but not the blocks themselves.
Right. Yep. Yeah, it's kind of confusing, but really the blocks are just data, and they don't, like LevelDB wouldn't be appropriate, I think, for storing just like big blobs of data, but for the indexes into that data, then I think it makes sense to use something like LevelDB.
Okay, thanks.
Yo. Address index. Yeah, are you for it or against it?
I'm asking you.
Am I for it or against it? That's a deeply political subject. I won't go on the record. I think it could be cool. I think there's some pretty good utilities now for doing opt-in indexes, and I think it would be really nice to have some additional indexes that we could just kind of flip on. I think that would be really, really convenient, but the obvious trade-off is that that's more code to maintain, that's more stuff in core that we have to look after, so there are good arguments both ways. The question is sort of, for anybody who doesn't have context on this, adding additional indexes to Bitcoin Core that aren't absolutely necessary for operation of the node is kind of controversial, because we probably don't want more in core than there needs to be, because the review burden is very high. Cool, thanks.
All right, thank you very much.
Hey, so just to continue a bit on what James did, focusing more on the build system, also a bit about unit tests, and then wrapping up with deterministic builds. I'm Marco Falke. I also work at Chaincode Labs in New York City. The build system is based on auto tools, so it should just work anywhere where auto tools runs. You just type in autogen, configure maybe some options, and then make, that's it. Very recently we added support for MSVC builds, mostly for Windows developers to do native builds and not having to switch between Linux and Windows all the time. And then for our release builds, we use cross-compilation, which is currently only supported on Ubuntu. To look a bit about all the modules and targets that our build system supports. So James was talking about regions, and then for the build system. They're called modules. There are some basic modules like util, which take care of logging or just random number generation, or crypto primitives, which provide hash functions. So we have Bitcoin CLI, which is one build target to just provide an utility command line interface to speak with a Bitcoin server to ask for maybe the chain state, maybe mempool state, maybe wallet state. So this one depends on the basic modules. We do have some libraries included directly in the as a subtree, mostly, so either for convenience, we include Univalley, which isn't commonly distributed on major distributions, so we include it for convenience. And then we also include the elliptic curve library and LevelDB because they are consensus critical. Then we also have dependencies on just general system libraries, for example, OpenSSL, which we use only the random number generator, libwind, or we use Boost for advanced C++ language features. Then another build target all the way on the left is Bitcoin Consensus, which is some sort of long-term project. It was designed to provide just a library that takes care of all the consensus that's going on. And then you could, for example, have your node, and then for some reason consensus changes, maybe there's a soft fork, maybe there's a hard fork, then you only update your library and you're running the latest consensus, but you don't have to upgrade your whole company infrastructure on, like, for example, you don't have to update your RPC interface, etc. But right now, Bitcoin Consensus is really minimal. It cannot deal with anything that is stateful, so it can do some stateless checks, such as simple transaction verification. So we do have another target, Bitcoin TX, which is a utility to modify, create or modify transactions. And then finally, all the other targets. This list is not exhaustive. All of them pretty much depend on everything, which is the Bitcoin D, the server, the daemon that runs in the background, or the Bitcoin Qt, which is the GUI, and then finally a ton of test binaries, which also depend on pretty much anything. A bit about testing. So I'm not going to explain testing in general. There are obvious advantages of testing, but for Bitcoin Core, the most important reason, in my opinion, is that we need to have some harness to check that consensus rules do not change accidentally. And then the other advantages, such as the design feedback loop. When you write a new feature, it gives you some feedback or a hint how to document that. And then finally, the nice environment fuzzy feeling when Travis is green. So Travis is the continuous integration we use on the GitHub project. But actually, when Travis is green, it's pretty much meaningless. I will explain later what it means. So to jump into some testing issues, if you look at the coverage we currently have, we have pretty good line coverage and function coverage, which is greater than 80%, but then branch coverage is around 50%, and then path coverage I couldn't get a number on, but I assume it's something like 0%. That is just because when you have a really large program, a lot of lines of code, a lot of branches, you can never get full path coverage, or it's almost impossible. So for example, look at this 2-line program. Let's assume it's the only function. So you call this program once, then you have 100% function coverage, and you also have 100% line coverage. But for branch coverage, it depends on what you pass in for those booleans. You could run it once, then you have 50% branch coverage, and then for path coverage, it's even worse. You'd have to run it 4 times to cover all of the possible paths, where you run, let's say first you run A and then X, and then you could also run A and Y, or B and X, or B and Y. And then just adding another line to this program in the same fashion makes it 8 paths, and it's going up exponentially, and it's impossible to test all of these cases. So even if we had full coverage, Dijkstra said you can only ever show the presence of bugs. You can never prove that there's no bug. So in addition to tests, we need some sort of like other tools or techniques to prevent accidental changes to the consensus behavior. What we do is maybe be reluctant in general towards changes. So whenever there's something which seems unnecessary, just avoid it. Avoid to make the change. If there's something that needs, has some clear motivation, it needs to go through some thorough review process. And ideally, these two, it's not really clear what thorough review means. It's not clear how many people should look at it. And then even if people looked at it and acknowledge the change, it's not clear when enough people looked at it and when no one found an issue, it doesn't mean there's no issue. So in the long term, there should be hopefully a formal verification tool that just generally works and then can prove that the consensus rules at least didn't change. But this is mostly a research topic. There's, as far as I am aware, no practical tool to achieve this today. We do have some tools such as a scripted diff on the source code, which was contributed by Corey Fields. And basically, instead of making a huge change of all source files, you only provide the essential change in the form of a script, and then you run this script, and the script defines how the commit looks like. Or another way is build for compare, which was contributed by Vladimir, which basically does an object dump before the change, and then compiles the executables, and then does an object dump after the changes. And you can compare what changed in the object dump, and then figure out how that affects, like if it was wanted, if maybe nothing changed, which is usually great. But then even if nothing changed, you can only be certain that nothing changed for that particular compiler version you used, that particular architecture you run the compiler on. So it's also not exhaustive. To continue on this thought, so what is helpful for sometimes proving that a change didn't change the binaries too much is deterministic builds. There's a great website with all the information on it. Just to give one sentence of it, deterministic builds provide an independently verifiable path from source code to binary code. And to give just a really short advantages and a comparison. So let's take, for example, plain old builds. And you wanted to compare for build verification purposes. For plain old builds, there was no general way to do this, and you'd have to manually compare the disassembly. Whereas with deterministic builds, you could do this automatically and check for bitwise identity. For example, you could have a build server run the build script and then check if, let's say, you want to compare how the Ubuntu's PPA packages, when they are compiled, that they are compiled without additional backdoors. So you could run, in addition to the Ubuntu build server farm, you could run your own farm, build all the packages, and then afterward check for identity, and then maybe even sign off on these changes, have your build server sign off if there's no difference. Or to look at distribution, so with conventional builds, you could only meaningfully be signed by the release maintainer or the release build server if it's some automated script. Whereas with deterministic builds, these can be signed by anyone and hopefully by any builder. So you could have, for example, this build server, or you build it on your own laptop, you build it on your own machine, and then compare the results, and then sign the results. And then if maybe some of your friends want to run Bitcoin Core, they do not want to just trust some random website on the internet that they provide the correct binaries, or maybe they don't want to trust the Ubuntu PPA or the Ubuntu build server that they compile the right Bitcoin code without any backdoors or issues. So then you could maybe ask some friends, and if they signed the binaries, if they did these deterministic builds, signed them, you can download them from anywhere, compare them, and then check the signatures. Or ideally, you just go ahead and do all of the building yourself, and then also compare with your friends. To give some common issues we found with deterministic builds or reasons for unclean builds. The most common one is probably timestamps. Just when you run the compiler, it's going to embed the timestamp of the current system time somewhere in the executable. These are often easy to work around by just setting a constant timestamp. Other issues happen when the system you're building on has different tools or different libraries to build. For example, Python 2 version, Python version 3, which has a different implementation of the dictionary and then sorts the keys in the dictionary in a different order. So suddenly some parts of the resulting executable are differently sorted, and you get the different result. Of course, different compiler versions will result in non-deterministic builds, because different compiler versions, maybe they only embed the version of the compiler somewhere in the executable, and then it's going to differ in that way, or they have some different behavior to optimize the code, and then you get differently sized binaries or differently performing binaries, which are also going to be non-deterministic. Or some fun things like number of CPU cores you use to compile, which could happen, for example, if there are different modules and then one is going to finish earlier and it's going to be written earlier to disk, or in some way is differently sorted. that yields a different executable. And pretty much awesome for tracking down issues is this tool called Diffuscope, which was originally written, I think, by the Debian folks who also work on deterministic builds, but you can install it, I think, on pretty much any Linux system, also Fedora. It's on the Python package manager, and you can install additional dependencies with your own package manager. I find it really helpful. To give an overview of how our deterministic builds look like today. So to remind, it's this path from source code to binary code. As input, you have the source code, and then, of course, some sort of descriptor how to run the build. These need to be the exact same, of course, for all the builders. And then our GTN builds environment is currently Ubuntu 18.04. And anyone can run it, and in the first step, it's going to produce the executables for all the architecture. So for Windows, 32-bit, 64-bit, I think, Mac OS, then a ton of Linux architectures such as ARM, and a ton more. I think it takes on a single core to run this more than a day. And then we have another step. So Windows and Mac require that these binaries that you run on the system are somehow signed with a key that is also signed off by Windows or Mac or Apple in some way. So what we do is do a second step, create some detached signatures that work on those operating systems, and then do another step, which is really quick, and it just combines these detached signatures with the binaries and then yields the final binaries for the Windows and Mac operating system. And then to wrap up, just on some issues that we are currently working on, or just give an overview of the progress. So I mentioned we use Ubuntu for the build environment, which isn't ideal. So I guess we can be pretty certain that there is probably no backdoor in Ubuntu, because if there was, most people run Ubuntu, and if they run a non-backdoored Bitcoin Core Ubuntu, it's on a backdoored Ubuntu, it's not really going to help. But it would be great to just have a way to pin the compiler version to just some defined version, because if Ubuntu were to change the compiler version of the environment we are currently using, we can no longer easily reproduce all the builds that happened in the past, because different compiler versions means different executables. And this indeed happened, I think, for Bitcoin Core 0.12 or something. Then another thing is where we do these detached signatures. Right now, it is done for each operating system by a single person, so there's some kind of like bottleneck. Would be nicer if it was distributed, so the trust would be somehow spread out. Could be achieved with distributed RSA. And then this have multiple maintainers sign off on the binaries. But what works already today is, of course, all the intermediate GTN build results are signed by a lot of people that build them. All the signatures are put in a repository, and everyone can and should compare them. That concludes my talk.
Are there any questions? All right, well, thank you very much, Mark. We're running a little bit of ahead of schedule, so let's take like a 15-minute break maybe. Continue again at 4:20. 少し早いので、少し15分の休憩を取ります。続きは、4時20分から。 So we still have, like yesterday, we still have a bunch of lunch boxes left over, and yesterday we had to throw some away, which was kind of wasteful. So if you want to eat some more or take some home, feel free to do that, please. また弁当はすごく残ってるので、昨日もちょっと捨てられたものもあるので、すごいもったいないので、ぜひ欲しい人が持って帰ってください。まあ、それともここで食べてもいいよ。
Test, test. All right. All right, I will be talking about Python Bitcoin lib. First, I'm going to start with an introduction slide. This is because I keep forgetting who I am, so I have to write it down in all my presentations. No, actually, first, before I get started, Python Bitcoin lib, there's a presentation right after mine that's about lib Bitcoin. That's actually a separate project. This is Python Bitcoin lib. Sorry for the ambiguity, but it's not my fault. So anyway, Python Bitcoin lib is a library of Python classes, functions, and other little helper methods for representing, parsing, and serializing Bitcoin data, running Bitcoin scripts, evaluating Bitcoin scripts, and it's a Python library. It's very useful for application development, for testing, things like that. Before I get too deep into this, I'm quite curious. Can I see a show of hands for who actually writes in Python in this audience? All right. Okay, thanks. So anyway, Python Bitcoin lib is useful if you're doing like rapid application prototyping or something. It's not a full node implementation. It's I suppose you could, in theory, make a full node implementation from it, but there's a lot of pieces missing. So anyway, it's not a full node. I believe originally this was started by Jeff Garzik as Python Bitcoin RPC, and then it like evolved over the years, passing from maintainer to maintainer, or fork from fork, or fork to fork rather. And there's also a few other forks flying around called Python Bitcoin RPC. One, I believe, made it into the Bitcoin Core repository for testing of Bitcoin Core. There's a lot of Python scripts there. But anyway, that's a separate branch and separate evolution of the library. And Python Bitcoin lib itself is currently, I guess, hosted under Peter Todd's repository, and he is ostensibly the maintainer, although he warns that it will go unmaintained very soon, or already has. So that's something people are going to have to deal with. But
Yeah, I mean, Peter has been more interested in Rust lately, which I'll mention in a moment. So what does the library have? It has some of the basic data structures you would expect, such as representing transactions and blocks. It has a basic ability to represent keys and secret keys and things like that. Also opcodes and scripts. It can represent scripts into a sort of parsed abstract syntax tree sort of format, or really it's not even a tree, it's a list of operations. It can evaluate scripts and verify them as well. And also it can serialize data, it can construct certain network messages, it has basic ability to interface with RPC. Right, so it just has a bunch of grab bag items and fun things you can do. So in Python Bitcoin lib, there is a distinction between mutable data structures and immutable data structures, which is a little odd because Python is generally considered to be not the right language to use if you want to preserve memory correctness, which you generally do want to do when you're dealing with Bitcoin. But anyway, I mean, the theory behind this is that if you're going to handle transaction data in Python or any other language really, at least you want to try to mark which ones are like final and aren't going to be modified. So in Python Bitcoin lib, that is C mutable transaction, and then just C transaction is the immutable version. Where if you create a C transaction and you initialize the data structure with a list of transaction inputs and a list of transaction outputs, then the C transaction type is not going to allow you to add extra inputs because theoretically that is, you've already defined the transaction and the transaction should not be able to be updated after that point. Also, Bitcoin Core shows transaction and block hashes as little Indian hex and everything else is big Indian hex. So there are some conversion tools to be able to play around with data, and this is very useful if you're ever on the command line just playing around with Bitcoin stuff. So X is the function for big Indian hexed bytes. Since it's used so often, it had a one-letter name, but this is really terrible if you're in a habit of using one-letter abbreviations or names for your variables when you're doing rapid prototyping or testing. So just be aware that X is actually a function. And then similarly, there's a function to go the other way, which is little Indian hex to bytes, or in bytes to hex, and hex to bytes, and things like that, and bytes to little Indian hex. Okay, so the library helps you use both testnet and mainnet. So the way it does that is switching through a function called select params. Signature hash, that's for transaction signing, and hashing the transaction in the correct format so that you can go and sign it. I believe it actually does have transaction signing capability using OpenSSL, although you should probably not intend to use it for that purpose. Perhaps for testing it's fine. Verify script seems to be consensus correct. You can run a script through it and check whether or not it ends up returning true or false. There's a bunch of unit tests, and you can do pay to script hash, like for multisig, although it doesn't implement BIP32. For that, I often I use PyCoin's BIP32 node implementation when I need to use BIP32. So there is an RPC library for communicating with Bitcoin nodes, or in particular Bitcoin Core. I have often found, though, that I've needed to write a wrapper around the RPC connection function, especially if you ever use this in like a high volume environment where you're rapidly or in succession querying Bitcoin Core, the RPC, because there's like an RPC thread limit, and sometimes you just need to refresh the connection. So often I write a decorator that around this RPC make connection or any RPC call to refresh the connection in the event that an error like that occurs. One interesting thing to note here is that when you're developing an application that uses Bitcoin Core, you should be careful not to treat Bitcoin Core as a database, because it's really not a database, even though some of the RPC interfaces used to kind of pretend it was, especially around accounts. accounts were a good example, because if you issue an RPC command to change an account, like I guess a benign one would be to change an account's name or something. It's not really a transactional interface like you would with a Postgres database or something. So in the event that other things in your software stack have failed, you would have to manually go back and fix all the things that you've told Bitcoin Core to do. There's no transactional atomicity guarantees or whatever. I'm not going to talk about that. Okay. Another useful thing in here is sign message and verify message. This is very useful for like audits or proving that you have control over a certain key. It uses, it's not just signing a message directly or a hash of a message, but rather there's a weird prefix. And this isn't the fault of Python Bitcoin lib. This is just a Bitcoin Core thing. If you want to comply with the sign message, verify message standard. And in fact, there's a new standard being proposed for, especially for like pay to witness pub key hash stuff or whatever. Because in certain situations, you need to be able to prove that you have control of certain output or whatever. And sign message doesn't actually support all those scenarios. You need to, your wallet software needs to know how to produce those signatures and verify those signatures. Anyway, one of the reasons why there is a prefix is so that you can't do attacks. Like if you just ask an arbitrary user, hey, sign this message to prove you have control, and oops, it's actually a transaction that you just signed that spends all your coins to me, you know, that would be a pretty bad vulnerability. So anyway, having a prefix makes sense. Also, it uses something called ECDSA pub key recovery. This is an interesting thing. I know it's completely off topic, but in Ethereum, if you've ever looked at the Ethereum transaction data structure, it actually has no, unlike Bitcoin, it doesn't use UTXOs, it uses credits and debits, and there's actually no from address. The address from which an account is debited in Ethereum is derived using ECDSA pub key recovery, similar to signed message in Bitcoin, to derive the from account from the signature on the Ethereum transaction. I regret knowing this. I don't want to know this, but anyway. So anyway, we can sign messages and prove it. The URL at the bottom of the screen is an example of using sign message and verify message. So I'm going to walk through an example of spinning a pay to pub key hash output. And so this scenario is that if you are paid and then you want to spend the money that you were paid, this is an example of how to go about doing that using Python and Python Bitcoin lib. So this page of code is just setting it up and importing all the required functions and libraries and tools. Line 25 on the screen, if you can see it, it's the longest line on the page. It's importing some of the script opcodes. Op hash 160, I mean, this is pay to pub key hash, so there's a hash in there, right? There's a check sig because you want to check the signature, whether it matches. You need to do a signature hash because you want to sign the transaction, or sign the input rather. Next line, you know, you have a verify script because you want to actually check that this is actually working. Also, it's select params mainnet because it's on, you want to use mainnet, not testnet, because that's where you were paid. Next slide. Before we begin, transactions have inputs and outputs. So if you're spending this input that you were paid some Bitcoin, so now you want to spend it. So the transaction that you're creating to spend your money that you've earned is going to have an input. For the sake of an example, we can just arbitrarily say we were paid with this transaction hash ID. And then the next one is the index in that transaction, of course. Right, anyway, and then at the very bottom, we're creating a transaction input based off of that transaction ID and the index. Next slide, and then we also have to make the script pub key, and then also we're going to make a transaction output because we're spinning it. And so again, this address is provided by whoever we're spending the money to, so that's not our data. And then finally, we're making a mutable transaction, and that's because obviously we're not done creating the transaction. We can have these inputs and outputs, but if you notice, the input hasn't been signed yet. And anyway, then you have to actually figure out what are you signing, and so that's what the signature hash is for. You sign the script pub key from the transaction, and we want cache all because we want to ensure the transaction doesn't change. This is pretty insecure. Don't do this in production code. I mean, this is using OpenSSL under the hood, but I mean, for the sake of testing and examples and demos, it's about as good as you're going to get. It's just an arbitrary function. Well, not arbitrary, but anyway, it's just sign this, please. So it produces the cryptographic signature, and then you can add the signature to the actual script sig on the input. And like line 70, I mean, you know, you've already created the transaction earlier at the top line of this slide, but now we're modifying it by adding a script sig. So that's why it needs to be mutable. Right. Okay, and then we can verify that the script sig works based off of the script pub key for that input, and in Python Bitcoin lib, it'll just fail with a raise an exception or whatever. So I'm not going to catch the exception here. It's just out there laying around. And then finally, there's a serialized method at the very end to serialize the transaction, and you want to convert that to hex because serialization always produces bytes, and you want some pretty printed hex so that you can go and copy paste that into send raw transaction or whatever on the Bitcoin Core RPC interface. So some things notably absent from Python Bitcoin lib. If you're going to implement something related to SegWit, don't, because there's nothing implemented in there to handle SegWit. So that's something important to note. It doesn't have Betch32 from BIP 173. It doesn't have BIP32 support. Doesn't support BIP 174. Doesn't support output descriptors, which I recognize we haven't talked about this past 2 days. There's no proposal, no generally accepted proposal yet for script version 2, which interestingly enough will actually be probably called script version 1, which is very confusing, but that's because Bitcoin script is currently version 0. These guys are laughing over here, but it's actually a huge problem. It's very ambiguous. Why is it still using OpenSSL? Who knows? Well, I mean, in general, for signing, I mean, the signature is still going to be correct no matter which of the two libraries you're using, but perhaps an ability to switch out between the two. I mean, that would be an interesting project to go implement, like a simple weekend thing or something. So anyway, that's all. That's Python Bitcoin lib. And just to be clear, that's not libbitcoin. Thanks. All right, any Python-related questions?
So just to make sure that I understand, this is completely different from Bitcoin D. It doesn't need it to be.
That's correct. This is not related to Bitcoin D, although the RPC interface would, if you want to communicate to a Bitcoin node on the other end, it would be Bitcoin D.
Okay, so when I look at this, it seems like a great learning tool for me. But who else uses it? What are the use cases?
Well, I mean, for example, I've used this in many projects for application development for everything from like making exchanges, for handling deposits and withdrawals, for handling any sort of time that I've handled Bitcoin transactions. I mean, my two main options have been either write something in Bash with the Bitcoin CLI create raw transaction interface, or you can use some other language other than Bash. And why would anyone want to write in Bash? So, yeah.
Okay.
So I'm one of the people working on Bitcoin JSLib, and SegWit support is really hard, so ganbatte.
Oh,
Good luck.
it's not my job.
So it sounds like people are using this for production code.
Yes.
And it's kind of scary that you mentioned that it's probably already unmaintained and it doesn't support all of these things.
Yes.
So what is the history of maintainership?
Poor.
I don't know. Okay. So I think here's an opportunity, if you are into Python, this is a way to get involved in Bitcoin development.
Oh, sure, absolutely. I mean, yeah. So I mean, in general, it's considered a bad idea to use unmaintained code. But at the same time, though, I mean, there is a collection of work that has been performed here that could be useful. I mean, some of the data structures are quite basic and like they're not going to be deprecated. So there are bits and pieces that you could probably safely use. Other parts that you should probably stay away from. Unfortunately, this requires expertise to tell the difference. So,
if someone is good at Python, who could they talk to about like reviving this as a maintained project?
you know, feel free to talk with me or Peter Todd. He's also he makes himself available. So those are the two starting places I would recommend. Thanks.
All right, thank you very much.
Okay, so I think this is the last session today. So thanks for holding out. I know it's been a long 2 days. So what I'd like to do here is, so I've done some documentation for LibBitcoin in the past half year, and as I work myself through up the repository, I learned more and more about the APIs, and it just gave me an opportunity to write some examples, hopefully, and provide a practical introduction to the Bitcoin as a developer tool, but also as, I would argue, a great learning tool for people who are starting out in Bitcoin who want to develop Bitcoin applications. So Eric's actually here for this session, so I think at the end of it I can defer some of the more detailed questions to him. But yeah, hopefully to give you guys just an intuition of what you can do with the Bitcoin starting out. So those are the things I'd like to cover. I'll give a brief overview over the toolkit overall. A quick comparison. Sometimes it's confusing, like what is LibBitcoin really? Is it a toolkit? Is it a library? Is it a server? It's all of the above. So maybe we can do a quick comparison of the server versus Bitcoin D that most of you are familiar with. And then we have like the BX, which is like a power tool, a command line power tool, which allows you to script scripts. It's got hashing functions in there. It's got server query tools in there. And also the base LibBitcoin system library, which contains most of the consensus code in there. We've got the LibBitcoin server, which is pretty cool. And we'll go over a very basic, maybe like your first LibBitcoin learning app. We'll go over one of the examples there. We can talk about scaling and the upcoming version that Eric and the maintainer team is working on. Okay. So quick intro. Currently maintained by Eric Voskuil, initiated by Emery Taki, as you guys probably know, and one of the first, or the first alternative implementation to the Satoshi or Bitcoin D prototype. One of the things that brought me to LibBitcoin is I'm not a great C++ ninja, so the readability of LibBitcoin was a great bonus for me. It's really, the code standards are well maintained. It's pretty readable for a C++ novice, And there's certain protocol logic that's just laid out very, very nicely. So I highly recommend that for people or students of Bitcoin. There is a certain design philosophy around performance on the server side, which is pretty cool. We can go into it in a little more detail afterwards with a couple examples. And on that front, also scalability. I can also provide some examples there. So on the left side, you have all the, if you will, separate modules of the Bitcoin laid out. And the arrows kind of indicate the dependencies. But the nice thing there is they all have their independent build system. So if you want to use a specific part of it, you can pull it out and do so. The ones which are in blue, let me start with the one at the bottom, the Bitcoin system. That's just a huge collection of classes and methods that allow you to build everything from like wallets to light clients. That's all in there. And as we move up the left side, that's kind of like the client stack. We've got the libBitcoin Explorer. That's a command line tool that offers online functionality and also offline functionality. And so that's kind of the great reference client implementation for libBitcoin. And on the right side, we have these kind of like the server stack, which ends up in a performance server application. Okay, so coming from Bitcoin D, I've got three things kind of lined up here. I've got the Bitcoin D RPC, JSON RPC interface on the left, and we've got the Bitcoin server right thereafter. We've got the Bitcoin command line explorer in the second from right, and finally we have the libBitcoin system kind of exposed to the right. So coming from Bitcoin D, you can kind of see how that maps over. Arguably the chain function, chain subscription, chain query, those you'll find in libBitcoin server. For the other parts like block generation, PTP, the actual wallet app, Bitcoin doesn't actually have, libBitcoin doesn't have a wallet app per se, but it does have pretty cool wallet functionality. We saw some of this stuff in the HD session yesterday. And so you'll find a lot of that either as a command line command, a BX command, or you find the corresponding class or methods in the C++ library for you to use. Wow, I just noticed that you guys translated the detailed version. That's awesome. That's a lot of work. So for your reference later, you can probably find what you're looking for coming from the Bitcoin D side on this overview here. One thing to note is the interface that we use. So on Bitcoin D, as James mentioned before, we have the subscription stuff over the ZMQ sockets, and the rest via JSON RPC. On the libBitcoin side, we use ZMQ for both subscription and query. I will go into a couple of examples later, but just to highlight that. Okay, so one of the obvious things when you compare the server stack is just the, I guess maybe the design philosophy, or it's just the way you expose it to a public client. So if I'm running Bitcoin D, you can probably argue that's kind of designed like a comprehensive local app for an end user. I've got a node in there. I can query the server. I have my own wallet. I can generate my own wallet from the Bitcoin D application. But if you want to expose it to, let's say, public clients, you probably want to throw a RPC app in between that adds authentication or some kind of security that you want to pad it with. And so the libBitcoin server itself uses the ZMQ socket framework for that, which includes the curved CP security. I think it's 256-bit security. And we're going to go through a couple examples there, but it's a pretty nifty framework, which also provides great scalability. One of the things about the ZMQ sockets, they're kind of like, they allow for non-overlapping lifetimes of these sockets. So if you're doing like a distributed system where elements can come and go and you want good recoverability, that's a fantastic framework. So scalability is obviously one of the, security scalabilities are one of the benefits for running a public server like the Bitcoin server. Okay, so I have some examples. The following examples are mostly around the command line tool and some basic libBitcoin system classes and methods. And you guys got an intro yesterday on most of this stuff, but I think it might be valuable to see how that looks like in libBitcoin. Oops, sorry. Okay, so here's a quick one. I do recommend, if you guys are not too familiar with EC Math, to run this at home, but you know, LibBitcoin has all the classes for demonstrating the basic properties of the EC Math that you need in Bitcoin, scalar operations over finite fields, and EC operations. And so, for example, here we're creating a seed, and we're generating a secret from that seed. We can demonstrate distributivity over a scalar, right? So here we're doing the left side, A plus B. Now we've calculated the left side. We are calculating A times C, which is part of the right side here of the equation, the second part. And as you add those up, you can demonstrate that, yes, this and this equate to the same thing. Very basic stuff. And of course, also operations over EC points. Same applies here. Distributivity, right? So A plus B times the generator point gives us this left side. The A point, and adding the A point to the B point gives us this, which we should be able to verify is the same. Yes, same point. Okay. So that's EC Math. The same you'll find in the C++ libraries. So what I'm looking at next is, you know, a basic transaction build. This is an example where I'm spending pay to pub key, hash, output to 6 different outputs. And so what I've done here is I've kind of stripped it everything, kind of like a bash program that you guys can follow. And all the commands you'll find here, so mnemonic to seed, creating the keys here. This is the spending key that we're generating. And then here, this is the UTXO, that's a typo, UTXO that I can spend from. So those are test coins on there. And here I'm generating all the output keys with the HD functions, HD key functions that BX provides. And here, I am building the output script. It's pretty straightforward. I'm calculating, this is pretty interesting, so I'm calculating the minimum fee that is required for it to be accepted by the server. So you can have a closer look at this, how the sig ops are summed up, SegWit and without SegWit. Okay, and here I'm constructing my transaction with the outputs. And then here, with a very basic online command, I can fetch the previous output script that I'm spending. Oh, I hope I'm online. Okay. Yep. And then we sign it. So let me just double check I am online. Sorry about that. Yep, I'm online. Okay. We sign it, and then we build the final transaction with the input script. And, sorry. And then we can validate and broadcast. Let's see if that works. Yeah, the kernel might have frozen there, but you guys can do that at home. Okay, so here's another one. So this is a pretty cool. You can use the eternal script machine from LibBitcoin to kind of validate your scripts and really see how the scripts execute. And so the example here is a pay to witness transaction wrapped into a pay to script hash output script. And so what happens is you basically have 4 individual script runs. Then the pay to script hash is recognized, and the embedded script is run, and then the witness script is recognized, and then the witness script is basically run on the script machine. And so I think I should be. Sorry, the kernel's all died on me. Sorry about that. Okay, so I'm fetching the previous output script I'm trying to spend. I need that for validation, obviously. So here I've pasted my transaction. That's the pay to witness script, pay to witness pub key hash, wrapped in a pay to script hash script. And then when I run it, oh, fantastic, there we go. So when I run it, I can actually see the individual script runs, right? There's the operation that was conducted. That's the operation right here. So basically a data push. And then here I have the stacked after that respective operation. And so you can kind of go through that, and if you have your own script that you want to debug, that's a fantastic tool to use. Okay. So onto the libBitcoin server. So as I mentioned before, the interface that we use is the ZMQ socket. There are two different types. There's the ZMQ publisher socket, which you just connect to, and you automatically receive updates. And we're talking about new blocks, new transactions, which are accepted either to the mempool or to the init block itself. And there's also a heartbeat you can subscribe to, and that's pretty nice because sometimes you might want to know whether the server is still alive at a higher frequency than, let's say, blocks are broadcasted. So that provides you with that information. In terms of the chain query, there's one thing I'd like to point out. libBitcoin indexes also by address, and we're going to run an example where we use that. So you can actually subscribe to notifications regarding an address, whether something's being spent to it or whether it's spending a UTXO. Or whether a UTXO of an address is being spent. Let me see what else is there. Yep, that's about it. And so maybe some of you are pretty familiar with ZMQ, but this is how a basic ZMQ socket kind of works. So as I mentioned before, the lifetimes between the server and client sockets don't necessarily have to overlap. So all the connection stuff is abstracted away. So your application doesn't really see whether an actual connection is happening. What you do is you connect to a port, you connect to your endpoint without really connecting it, right? So right now nothing's happened. You just told your socket, I would like to connect to that endpoint. I have yet to specify what message I'd like to send. When you send the message, that message is then put onto a queue, which is internal. That is invisible to the application. And that queue is then sent whenever the socket can establish a connection with the server socket. So maybe your server socket is dead right now. You've sent something. And once that server socket comes online, that message then is dequeued and then sent over the wire. Same goes for receive. So receive is in this case, a blocking command, but I can receive a message and I can dequeue it. And the way ZMQ messages kind of look like, they have these little frames, and we have a format for libBitcoin. You have the command, server command, the message ID to be able to correlate the queries. And we'll see in a second why that message ID is pretty useful. That is returned in the response. So if you send a message ID, you will get the response corresponding to the same query ID. And of course, the query and respective response payload. And so here's why that message ID is useful. You can connect to the server socket, which is a ZMQ router socket on the libBitcoin side, with either a requester or a dealer socket. So the requester socket is a little simpler to use. It is synchronous. So for every query, you get a response, and there's no other pattern that you can use. For the dealer, on the other hand, you can send as many queries as you want, and they will be received asynchronously. The dealer also allows you to connect. I'll show you in a second. So here are the subscription services that libBitcoin provides. So the libBitcoin server provides a heartbeat, new blocks accepted to the strong chain, and new transaction, either mempool or included in a new block. So you just connect to that. You connect to the publisher, and you'll receive updates automatically. The heartbeat, as I mentioned before, is pretty nice. If you don't receive an update, I don't know, in X seconds from the new blocks service, that's a nice way to know whether the server is still online. And of course, you can subscribe to multiple services with a single socket. In terms of security, so what you do is the server socket, for example, will have a public key that is known. And so you can authenticate that you're connecting to the server that you think you are. And you can generate your own private key and public key for every session if you want, or you can reuse that. And that enables you to connect in a encrypted fashion. Conversely, the server can also host a list of client public keys, which are allowed to connect to the server itself. Okay, so I can show an example there as well. So here's a simple example of connecting to the server and requesting the latest height of the strong chain. Here's the diagram of the CMQ socket we were using before. We create a context, one context per process and thread, and we instantiate our ZMQ requester socket. So this is synchronous only. And right here, as I showed before, we have the public key, the curve CP public key of the server that we're connecting to, and that way we can authenticate that we're actually connecting to the instance that we want to. And we're generating a new set of keys for our socket to derive the encrypted connection that we'll use later. So that's base 85 encoded, and that's what we're using for this session. Okay. So I'm connecting my socket to the endpoint. That doesn't mean I'm actually making a connection. That happens in the background. And here you see we're gonna send that request. This is the message format. That's the response format. Here's the request message. That's the command right there. Fetch last height. That's the message ID. And, yep. And here we're setting up the response message objects right here. And what's nice about using the same base library as the server side, for example, here we're dequeuing the response payload, and there's some pretty nice stream methods that I'm using from LibBitcoin to dequeue the error code and the height encoded in 4 bytes. So let's see if that works. There we go. So the query went through, success, and we have a return block height down there from the testnet. Okay. Okay, so finally, I'd like to give an example of what you could build as a first project, for example, with the Bitcoin. We're going to build like a SPV-like client, a wallet, and we're going to build one that queries the public API of the Bitcoin, and we can do that because addresses are indexed, so I can actually receive notifications if an address that I control receives money, right? And I can build my Merkle proof. I can check and validate whether that was actually included in a block. So what's an SPV client? So an SPV client basically validates the header chain. It validates the proof of work, but does not actually validate the entire block itself. So in the Bitcoin, it would kind of look like this. I would have my headers. I would request those headers from a server. And there's this object called chain state, which is pretty nice. The chain state takes every subsequent header and it kind of promotes its state to the next chain state. And one thing that it allows us to do is to understand, okay, so is the difficulty in that header actually correct, right? So the difficulty of that header at a certain height is implied by the history of the header chain. And so that's kind of how we validate the header. We want to make sure that the proof of work conducted at every height is indeed valid, right? And that's all the light client does. So I've got an example of that as well. Let's see if I can get that to run. Cool. So that's right here. And this is, again, all with the LibBitcoin system library, very, very basic. Okay, so I'm setting up my ZMQ socket, setting up my Genesis block data. Yep. And what I'm doing right now is I'm requesting the header at every height, right? And every height, I take that header, I generate my new chain state at that height, and check whether the proof of work difficulty at that height was indeed done correctly. Okay, so it's just going through the entire chain right now, but what it's printing out is at every height you have, let me stop it real quick. It has the header hash, and it has the target difficulty right thereafter. And at home, or when you have time, when you let this run for a while, you'll see how the difficulty retarget actually occurs, and you can visually observe how the headers are always below the difficulty, target difficulty that's printed out there. So that's all it does in terms of chain validation. Okay, so back to our SPV example. Now, if we want to then confirm that we've received money, right? We haven't indexed any transactions. We've just validated the chain, the header chain. What we now need is some kind of information from the server that somebody has sent money or funds to an address that we control. And we do that through subscribing to specific addresses in LibBitcoin. And as I mentioned before, because the LibBitcoin server indexes by address as well, we can do that. We don't have to do this over the P2P interface, public interface. Let me see if I can make this work. Okay. So the way this works, so again, I'm making a query to the server, but this time, I'm subscribing to a specific address, right? And so this is not a subscription in terms of ZFQ sockets. This is a asynchronous query. So it's now telling me, okay, the subscription to that address you want is confirmed, and I should be able to send a transaction and observe. This probably crashed. Okay, sorry, this kernel just crashed, so I'm going to skip that, but you can verify that yourself. Just run this script, send that helper transaction to this address, and you will see that you'll receive a notification that that address has actually received some funds. Okay. So finally, now that we know that we've received a transaction, we need to verify that it's actually included into a block, that it has been confirmed. And we do that through the Merkle proof. And so how do we do that? We basically request all the transaction hashes from that height of interest, and we validate the transaction that we're looking for is actually part of that Merkle construction, and then we can validate that that root is indeed valid. So there too we have last example for today. Okay, let's see if I can get this nice. That's the transaction we're looking to validate. Next, we're requesting the Merkle root from the header chain. So we're fetching the block header at the height of interest. Then we get all the transaction hashes of that block, because we need that to construct the Merkle block. And now we compute the Merkle root. So you can compare that root with the one we got from above, which is here, and they are the same. So we just validated that transaction is in that blocking is confirmed. Okay. So, yeah, so now that we've built our first light client or LibBitcoin application, we can start thinking about how that scales out. So for the publishing service, what can happen? So on the left side, let's say you have multiple clients subscribing to your publisher. What can happen is these messages can potentially be dropped if you have too many subscribers. That queues up on the publisher side, and they're kind of dropped silently. Thankfully, ZMQ provides a really nice tool to provide a proxy. You just bind the a XSub socket type with XPub socket type, and you can provide a proxy which allows you to scale out, as you see on the right side. So that's pretty straightforward for publishing services. For query services, let's have a look at one without, like a brokerless setup. So you've got some kind of load balancer that tells the client that comes online what the server-side topology may look like. And then the question is like, how do you distribute the queries? And let's start with queries which are kind of stateless. So the query that we had before where we're subscribing to a specific address, there's a certain session state that's implied, right? The server knows that I only want notifications pertinent to that address. But other queries like fetch height or fetch block, those are obviously stateless. They are not specific to that specific connection. So you can do round robin. You can have the client distribute the load, and so if you want to provide some kind of scaling solution for the address subscription we saw before, you can use a broker in between, and that broker kind of needs to track what server that subscription was requested from, because only that server instance knows what that client is looking for, which address is being watched. So that's it. So last slide is about version 4. So Eric and the maintainer team, they're working really hard on making the initial sync much faster. Maybe Eric can talk a bit about that later. But basically providing, once you've established the strongest header chain, the most proof of work, you start downloading the blocks in parallel, right? Not sequentially from the BOM. So you validate sequentially from the BOM, but you download them from the peers in parallel. Neil's working on the WebSocket interface. I believe HTTP and also JSON RPC is part of that work. So your front end or your browser will have an easier time querying the server directly. And there's also some work being done to parameterize the chain parameters so multi-coin support becomes a lot easier. So that's that. I hope I gave you a okay introduction, or at least intuition for what you can do with LibBitcoin and what it is. Server-side stuff, entire toolkit, command line for learning Bitcoin or scripting transactions manually. Overall, a great toolkit. Cool. If you guys have any questions. Yep. Thanks.
Hi, thanks for the talk. So a long time ago in a galaxy far away, there was a project called Dark Wallet. And apparently they were using the Obelisk server, and that kind of got merged into LibBitcoin because Amir Taki, worked on that. And I was just wondering, is that unmaintained? Because I noticed it was still in there, and you could technically run a Dark Wallet server using LibBitcoin server. Is it still maintained, or are you just kind of leaving it there like a little thing dangling off that you're not caring about?
I think Eric can give you the history on how that was merged into the current project.
Yeah, so the Bitcoin started out as several different tools for the support of the first dedicated exchange called Britcoin that Amir worked on with Phantom Circuit. And so we call the base library the system library. It's basically still that, utilities, type system. There was Obelisk, which was also part of that. It just had a different brand. And there was another thing called SX. Never really figured out exactly what SX stood for. Sexy, Spasmilo Expander, there's a couple guesses. But they were all part of one project, which we call LibBitcoin. And so to prevent this kind of confusion, I eventually rebranded everything under just LibBitcoin. So that's why we got 10 repos. One of them is LibBitcoin Server. You saw BX, that's LibBitcoin Explorer. So if you drop the lib, it's Bitcoin Explorer, Bitcoin Server, Bitcoin Node. Those are the only ones that have executables and config and command line. Everything else is just libraries. Those sit on top of their own libraries, so you can make your own if you want different config, which has come up recently. So yeah, it's always been part of the same set of stuff. Dark Wallet, different team, different project. Amir also worked on that. Dark Market, same thing, that was picked up by Open Bazaar. There's other dark stuff going on out there, but Dark Wallet has never been fully complete. There's another project that's kind of working on getting that complete now.
Eric said it's end of the year.
By the way, James is amazing. I would never have given you guys such a good presentation. I'm so glad he took it. But I have a lot more history. So V4, I've told people we're targeting the end of the year. Looks like we'll make that. The biggest item is the first one. It's a little bit beyond just initial block download. Continuous parallel block download it always works that way. So a lot of parallelism and asynchrony and fastness, parallel database writes, concurrent writes to the database of blocks, things like that. So it's not just parallel block downloads, kind of a big chunk of work. But most of it's done, and it's starting to validate, and that's really cool. The WebSocket stuff is another big chunk of work. What will probably happen if we don't get far enough along, it'll just be the WebSockets, then maybe HTTP, and then maybe the RPC compatibility layer for the stuff that we can support. We don't have a wallet, so we can't support all the JSON RPC calls that Bitcoin D does, but we don't intend to. The multi-coin support is basically done. The Feathercoin Foundation put some guys behind that, and so they're going to be in it. Litecoin, I think, is done. I think Bitcoin Cash will be in there. So basically, with configuration file changes only, you can run everything we already run. The wallet side, the BX side, and all the utilities, they already do. This is really just a question of expanding the configurability of parameters, constants that define node behavior.
Okay, I just wanted to point out, I want to thank Andito and Akio for translating all the slides. I noticed that must have been an immense amount of work. Amazing detail, attention to detail. So maybe just a round of applause for those guys.
All right, with that, it ends our workshop. So give yourself a round of applause. Congratulations. You have some work? Okay.
I hope you enjoyed all the material. It's a truly amazing effort. A round of applause for trainers, please. All the guys there. It's been a true privilege working with such an intelligent group of people. It was really an amazing experience, and putting together the program, and we try to make program diverse and cover a wide variety of topics. I'd like to also say special thanks to Brian Bishop. He had to step out, but he's done an amazing work with real-time disassembly of Japanese presentations back into English. I've never seen anything like this. I'd also like to thank all the sponsors of Scaling Bitcoin. Scaling Bitcoin conference is what enables Dev++. Basically, since everybody is here for scaling, that's what enables us to get together all the developers and assemble this program. We incentivize sponsors to participate in Dev++ through higher tiers. So we only list higher tier sponsors, but every sponsor and every contributor is just as valuable to this process. So a round of applause to everybody involved who have contributed to this event financially, please. And I'd like to also thank Digilab, Taro Watanabe, Andito, and the entire Digilab team who has been our host for this event. And it has been also a privilege working together. One of the most As you know, scaling and Bitcoin Age travels around the world. This has been one of the most competent teams that we have dealt with, and they do really amazing work in propagating Bitcoin and developing applications on top of Bitcoin, and it's really an amazing experience. So as you know, for next 2 days we have a Scaling Bitcoin event. A lot of you are coming there. If you're not and you change your mind, you can still get tickets. We have huge capacity for the event. And those who are joining, there's going to be a social event at 6:30. You can find information on the website. With that, the second installment of Dev++ is...
maybe one small thing. As mentioned on Slack, like all the material here and is freely available, and you can do with that knowledge as what you wish. Hopefully you make a contribution. Hopefully it's a positive contribution, but don't take us for the judge for it. So.
Yeah, it's publicly available. It's a CC BY license, so just attribute the material if you use it. Listen to it. We were not planning to do a live stream, but due to demand, we actually did a live stream with the kind of a camera position there. But we've recorded all these presentations. There's like 5 cameras in this venue with the 2 4K screens. I've never seen anything like that. And we will be, in coming weeks, once the dust settles, we will edit that in proper format, and all of this will be published on YouTube. So propagate the knowledge. If anybody wants to learn about everything that has been covered here, as well as previous events, just send them to YouTube, and we're going to try to continue doing this every year, and if possible, more frequent. So with that, Dev++ is closed. Thank you, everybody.